In 1989, two scientists made an announcement that stunned the scientific world. They claimed they had achieved something that shouldn't have been possible: nuclear fusion at room temperature. If it were true, it would mean a new source of energy. Clean, cheap, almost limitless. No extreme heat, no massive reactors, no stars. This moment marked the beginning of what later became known as cold fusion. And for a brief moment, it looked like it had actually worked. To understand why this mattered, you have to understand fusion itself. Nuclear fusion is the process that powers the sun. Under normal circumstances, it requires enormous pressure and temperature, millions of degrees. That is why fusion experiments are usually massive, expensive, and incredibly complex. Cold fusion claimed to bypass all of that. Instead of extreme heat, it proposed that fusion could happen inside a simple laboratory setup, on a table, at room temperature. If that were true, it would overturn decades of physics. The experiment itself was surprisingly simple. Chemists Martin Fleischmann and Stanley Pons used a container filled with heavy water. Inside it, they placed a palladium electrode and ran an electric current through the system. Palladium has an unusual property. It can absorb large amounts of hydrogen. Their idea was that hydrogen atoms would pack so tightly inside the metal that fusion reactions would begin. And according to their measurements, something extraordinary happened. They reported excess heat, more energy coming out than could be explained by chemistry alone. If correct, this wasn't just an anomaly, it was a breakthrough. Excess heat was the key. If an experiment produces more energy than it consumes, it changes everything. Cold fusion promised energy without carbon emissions, without radioactive waste, without the infrastructure of conventional nuclear power. The announcement spread rapidly. Universities, government labs, and private researchers rushed to repeat the experiment. This was the moment where cold fusion would either become real science or disappear. Science depends on one thing above all else: reproducibility. If a result is real, other people should be able to observe it using the same method. But when other researchers attempted to replicate the cold fusion experiment, the results were inconsistent. Most laboratories found nothing. Some reported tiny heat anomalies, but they were unstable and unreliable. Even the experiments that seemed promising couldn't be repeated consistently. The more carefully measurements were controlled, the smaller the effect became. And then, in many cases, it vanished completely. This was the fundamental issue. Cold fusion appeared to work once, or at least it seemed to. But science doesn't accept one-time miracles. Real effects don't disappear when instruments improve. As researchers refined their equipment and eliminated sources of error, the excess heat disappeared. No clear nuclear byproducts were found. No radiation consistent with fusion. No repeatable signal. Without repetition, the claim collapsed. By the early 1990s, the scientific community reached a conclusion. There was no convincing evidence that cold fusion produced nuclear reactions. Most physicists concluded the original results were caused by experimental error, miscalculation, or misunderstood chemistry. Funding dried up. Research programs were canceled. Cold fusion was no longer considered a legitimate area of study. Not because it was disproven dramatically, but because it failed quietly. Despite this, cold fusion never completely disappeared. Some researchers argued it was abandoned too quickly. Others believed the effect was real but poorly understood. And a few claimed it was suppressed. But belief is not evidence. Extraordinary claims require extraordinary proof, and cold fusion never produced proof that survived replication. cold fusion remains one of the most famous examples of how science actually works. An exciting idea is not enough. A single experiment is not enough. Even results that appear to work must survive repetition, scrutiny, and time. Sometimes an experiment seems to succeed, but reality demands consistency. And when consistency fails, even the most promising discoveries fade into history, quietly.